Path integrals. I know. It's something that strikes fear into probably every quantum mechanics student at some point in their lives. It's notorious for being like super hard to solve, and like people say it's impossible to solve for like most cases. Mathematicians hate it for not being rigorous for the interacting case, and it's just a mess. So the path integral formulation, despite the hate, is a very powerful tool in quantum mechanics and quantum field theory, especially when studying non-perturbative phenomena. Now, it's also really hard. It's a very hard topic to engage with. And I want to, today, try to make a video on path integrals that is in such a way where that anyone can understand. Anyone that has studied quantum mechanics in the past can understand. So today I'm going to try to use a bit of a different pedagogy compared to my other videos. I want to like work through each step, and I want to make each step very clear. I'm going to be repeating myself a lot throughout this video to make sure that some core concepts will actually make sense. So I want, because like push videos on path integrals are on YouTube, and honestly, I don't think, at least for me, I couldn't really understand them very well, except for Andrew Dodson's video. That's an exception. So I want to make a video that's very accessible to a beginner that has done a decent amount of quantum mechanics. You don't have to be a pro. You don't have to be an expert in quantum mechanics. You just have to just know how to solve the Schrodinger equation, know some of the Dirac formalism, and you'll be good for this video. I hope. So without any more further ado, let's begin. So a key concept used in the path integral formulation of quantum mechanics are what are called functionals. So we know that a function, a normal function, elementary function, or formal, normal. A normal function is just a mapping that takes in some number, let's call it x, and it assigns it some real number. We're talking about real valued functions and real valued functionals throughout this entire video, by the way. So a function just takes in one input, gives it an output, right? Pretty simple. Like f of x equals x squared minus 1 is a function because it takes in values of x like 1 and it assigns it a real number, 0. F of 2 is going to be 3. F of 3 is going to be 8. You got the idea. Now functionals, so this was like a normal function. A functional is a bit different. So a functionals, these take in, instead of taking in numbers as inputs, they take in functions as inputs. Let me use a letter G. So it's going to take in a function as an input and it assigns it a real number. So it's a function of functions, right? So before we'd had like f of x equals x minus 1, here we'd have, say, like g equals the integral from 0 to 3 dx f of x. Here's an example of a functional. G is a functional because it's a function of f, of course, right? It's a function of f, of course, because f is like in the right-hand side. It's a function of a function, and it's going to assign each function a number. Since we're integrating it, g is called a functional. And whenever we have a functional, we like to write the nested function like in these like brackets. So g would be called a functional. Let's give some examples. So f of x could be x squared. Just like how we could choose x to be 1 here, we found out that f of 1 is 0. Well, we can choose f of x to be x squared, and what's g? Well, to find that, we just have to integrate over x squared. The integral of x squared is going to be 1/3 x cubed, right? And we're integrating from 0 to 3. So that's just going to give us 3 squared, which is 27 divided by 3 is 9. So our answer is 9. So g is a functional since it took a function, x squared in our case, and to give it a real number, it assigned it a real number 9. But you can choose a different function. Just like how we chose a different number for the input for a function, we can choose a different function for a functional. We can choose the function x, or x minus 1. So g of f, for where f is x minus 1, is the integral from 0 to 3 dx of x minus 1. The integral of x minus 1 is just going to be 1 over 2 x squared minus x from 0 to 3. 3 squared is 9. 9 over 2 is 4.5. So our answer is 4.5 minus 3, which is 0.5, or just 1/2. So g takes in different functions and it assigns it a real number, just like how f of x took in different numbers and assigned it a number. So a functional is a function of functions that takes in a function, any arbitrary function in the domain, and it gives it a real number. Now, we can do a lot of things to functionals that we did to functions. Like, for example, we know how to take the derivative of functions, right? Well, we can do the same thing to functionals. We can take the derivative of a functional with respect to the function that's like in the input of the functional. So we can do analogous things to functionals that we did to functions. A very important thing is what's called functional integration. So we know that if we have, like, say x, here's f of x, or just here's f, then we have some arbitrary function f of x. We could integrate over the function, right? To get the area under the curve for, like, some values of x, like in some open set or closed set. So we could do that to functions, right? And this would just be written as dx f of x from, like, x equals a to x equals b if these points are called a and b, right? And we see that we are integrating over x since we're integrating like under the function between values of x. So we use the terminology, we integrate over x, all right? Or another word they might see being used is a space, integrate over a space of real numbers. So what's going to be the case for a functional? Say instead of f of x, we use the functional g of f. Now we'd have g of f, which is our functional. And for our x-axis, we now instead have some arbitrary function f, right? If we can have, again, we can just have some arbitrary curve, and then we can integrate under that curve to find the area. But instead of integrating between points, we don't have points, we have functions. Instead, we're integrating between functions instead. So we can have, say, the function f of a, and then f of b. Or f of a could be, like, say, x squared plus 1. And f of b could be, like, x cubed minus 3. So it's pretty weird how instead of integrating over like points, we're integrating over functions. So we say that we're integrating over, the word that we use is that we're integrating over a function space, or the space of functions, a set of functions, right? And we'd write this out as an integral of g of f over f, where f is a function. And we start out at f equals a, where a is like a function, right? Sorry, did I write f of a here? Yeah, sorry, yeah, never mind. So we start out at f equals f of a. Yeah, f equals f of a. To f equals f of b. Just like how here we went from x equals a to x equals b. Here we had f equals f of a to f equals f of b. And we call this functional integration. Now you might be wondering, how do we use this in the path integral formulation? Well, in the path integral formulation, we integrate over functions. So the path integral is going to be a functional integral. So to solve the path integral, we are going to be using functional integration. All right? So that's where this picture ties into the path integral formulation. Now for the rest of this video, we aren't going to be talking about the analysis of functional integration. For the rest of the video, we will just be deriving a path integral. But when we start solving it for some cases, like for the free particle, we'll be referring back to functional integration. So if you want to learn how to solve the path integral for some simple cases, you have to sort of like get down functional integration and just understand what we're doing. So yeah, let's now start to derive the path integral. Now, to be able to derive the path integral, there's basically just two things that we need to know beforehand. So one, you need to know the completeness relation, which is this. We call this the completeness relation. This is a relation that's used in quantum mechanics and quantum field theory a lot. And you can find an explanation for it in the textbook Griffith's Quantum Mechanics, and I think most common textbooks on quantum mechanics. But for a brief recap, this thing over here is called like this this like kind of weird thing. It's called the tensor, or the outer product, which is just the tensor product. So it's called the outer product. And what is the outer product? Well, say we have two vectors. So you have 1, 0. That's a boring vector to use. So yeah, like we have 2, 0. And we have another vector. Let's call this vector 3, 1. The outer product, or the tensor product, between the vectors 2, 0 and 3, 1 is going to be 2 times 3, 0 times 3, 2 times 1, 2 times, 2 times 1, and then 0 times 1. So it's going to be 6, 2, 0, and 0. So to find the outer product between two vectors, we just have to like multiply the inputs together in these corresponding spots. And the outer product is very useful since it allows us to form a matrix from two column vectors. So in quantum mechanics, we are interested in taking the outer product of these state vectors to get a matrix. So this would actually be the identity matrix. So it's not going to be 1 as in like the number 1. It's really going to be a matrix, the identity matrix. All right. And the second thing that we have to know is we have to know that if we have some vector A, and we want to expand A in terms of a basis, so you have Cn, En, we have to know that Cn equals En times A. So the coefficients is just the inner product between the basis and the vector that we are expanding in terms of a basis. So this might seem a bit weird, so let's just use a nice example. So a good example to use is spin, which isn't a statement said often in physics. A good example is spin. So for spin, we can have like a spin state. It's a superposition of spin up and spin down. So it's just some linear combination of up and down. All right. So say we want to isolate A. We want to solve for A in terms of our spin states. All we have to do is we just have to multiply both sides by the spin up state, but the composite conjugate of the spin up state. So let's multiply both sides by the dual spin up state, basically. So that's just A times spin up plus B times spin down times spin up. That gives us A times, this should be the dual, the covector spin up. So this just gives us A times spin up plus B times spin up times spin down. And the inner product of spin up and spin down is just 0. The inner product of spin up and spin up is 1. So we just get A. So this confirms our belief that to project out the coefficient of some basis vector, we just have to multiply the state vector by the dual version, the covector version of that basis vector. Now, of course, we assumed one thing. We assumed that we had what's called an orthonormal basis. An orthonormal basis is a basis where En, the inner product of En and Em, is the Kronecker delta Nm. And of course, if you get the Kronecker delta Nm, it's just going to be 1 if n equals m, and 0 if n does not equal to m. So basically, our basis vectors are at right angles to each other, and they have a length of 1. Then this whole thing works. So here we just expanded A in terms of a linear combination of basis vectors En, and Cn is just going to be En multiplied by the vector A. So like C1 will be E1 times A, C2 would be E2 times A. I'm using the word times, but when I say times, I mean the inner product, by the way. Times is just faster than the inner product or the dot product. So these are the two things that we need to know for this video. So the question that we ask to derive the path integral is pretty simple. We want to ask, or we want to find out, say that we have a particle that has a 100% chance of being measured at point A. So basically, we know that it's at point A. And say that there's some other point, let's call it point B. We want to find the probability that the particle starts at point A, and then we measure it to be at point B. So it's initially at point A, and then we measure the particle again, and we find out that it's in point B. How do we calculate that? Quantum mechanics gives us a nice recipe to calculate this, right? The Born rule says that to find the probability that it starts at A and we measure it at B, all we have to do is we just expand A in terms of a linear combination of basis vectors, and then Cn is going to be the probability amplitude. So basically, what this is telling us is that the probability is going to be the inner product of the states B and A, where the state vector A is the position eigenstate, it's at point A, and then ket B is just the position eigenstate for a particle at point B. So we have to calculate what this is going to be, and bam, we have our answer. So this begs the question, what is this equal to? The answer is 0. That's your answer. The inner product of B and A is 0. And yeah, you don't really need the path integral. We're pretty much done. Thanks for watching and have a great day. Just kidding. There's of course more to that. So for those of you that have studied quantum mechanics to a decent amount, you probably already knew that the answer is 0, right? Because A and B are position eigenstates, right? So their inner product is going to be 0 if A and B are different locations. And this makes logical sense, right? If you measure a particle at some point A, it's not going to instantaneously be at point B if you measure it like instantaneously again, right? It won't like teleport to point B. We have to give it some time for it to travel to point B. I use the word travel here in a light way since people can get mad if you don't use their interpretation. So when I say travel, I mean that it's going to take some time for us to measure the particle at point A, and then measure it at, and then it appears at B when we measure it again, right? So basically, we have to allow time to exist here. So the question that we should really be asking here is, what is the probability that the particle starts at A and then we measure it at B in time t. So it starts at A, some time passes, and then we measure it again, and we say, oh, it's at B. How do we calculate that? Well, it's a same thing, basically. It's going to be B, the inner product of B, and A of t. Now, here's the question. How do we actually find, like, what is it equal to? Well, to do that, we have to expand A of t. We have to expand that in terms of a time evolution factor called ut acting on the initial value of A. So ut is just the time evolution operator. It's going to time evolve our state for us. And the value for u of t is going to be e to the minus I ht. You guys might see it written as e to the minus iet, which is true in quantum mechanics, but we want to use the Hamiltonian for now to because it's going to help us out in quantum field theory. So we're going to use e to the minus iht, where h is the Hamiltonian, which will be our energy when we multiply it by an eigenstate and get our energy observable out. So basically, A of t is going to be e to the minus iht times A naught. So this means that our probability that it goes from A to B in time t, it's going to be B. It's going to be B e to the minus iht times A. This is progress. Of course, we went from like inner product of B with A to B with A of t to B with e to minus iht A. And of course, here we are defining A to be A at time t equals 0. So here is what we have so far. Okay, and it is progress since we've introduced the Hamiltonian. And for those of you who have studied physics, which is like all of you, you've probably at least heard of the Hamiltonian. And the Hamiltonian describes the dynamics of our system. Right? Different Hamiltonians describe different systems. So by introducing our Hamiltonian, we are introducing like dynamics of different potential systems. So this is a step in the right direction. So what can we actually do now? Well, what we can do is we can say that this is going to be equal. This expression, let me just erase this so I not make these cluttered. So this is going to be equal to b times e to the minus I h t over n raised to the nth power. This makes sense, right? Since this cancels out. But this, we get our OG expression. So why are we doing this, you might ask? It's going to make sense later. Just bear with me. So you can write the time evolution operator in this way. And this just means that we're taking the inner product of b with e to the minus I h t over n times e to the minus I h t over n n times and then times a. Right? So we're basically splitting up time into multiple time slices, right? So we're just taking in time and we're just splitting it up into multiple parts, and we're just multiplying all those parts together to get our OG expression, right? That's all we're doing here. So what does this correspond to in a physical picture for those of you that might be a bit lost? All we're saying here is that the probability that we go from A to B in time t is equal to the probability that we go from A to B in time t over n times n. That's all we're saying. So the probability that we go from A to B in 5 seconds is the probability that we go from A to B in 2.5 seconds plus 2.5 seconds. Basically what we're doing here. Yeah, all we're doing here. So we're just splitting time up into multiple time slices, or n time slices in this case. Now this term is like this expression here. It's kind of a sad expression, because in our first expression we had the time evolution factor act on one state, right? But for here, in this case, we have to multiply all of these evolution factors. They're all acting on A. Like, does A really deserve all that attention? It would be really nice if we could have each of these time evolving factors act on their own state. Just like how this one did. We had one of these factors act on A. It would be nice to have each one of these time slice factors act on their own position state instead of them all acting on A. How can we do that? How can we introduce something like that? Well, that's where our completeness relation comes in. Remember, we have to erase. Okay. Remember that the integral over dx of the outer product of x and x is going to be 1, right? We can use that, but in our case, let's use q1, q2, and q3, and so on for our positions, because reasons. So let's use the variable q instead of x. So we can just say that the integral of, actually, before we do this, let's use the case where n equals 2 for a nice example. So we'd have the integral, actually no integral so far, let's just do the bare expression. So we'd have the inner product of b with e to the minus I h 2 over 2 times e to the minus I h 2 over 2 times a. Then we do the integral over dq1. This is going to be equal to this integral over dq1 of b acting on e to the minus I h 2 over 2 times q1 e to the minus I h 2 over 2 acting on a. So this is what we were trying to do. We had two of these time slices. We don't want both of them to act on a. Like we can do that, but a doesn't deserve all that attention. Instead, it's nicer to have each one of these act on some state. So when we added in an extra position, it's natural. Like this, each of these time factors can act on their own ket, basically. So we are time evolving q1 with e to the minus I h 2 over 2. That's what we're trying to do. And we can do this. This is allowed because we're integrating over dq1. And remember that the integral over dq of q, outer product q of q and q equals 1, right? And that's what we have over here. This integral is going to be equal to 1. So the expression is equivalent to this one over here, which is in turn equivalent to this one over here. Progress, baby. We're making progress. So, what does this correspond to in the physical picture? Like, this is just some abstract math. What does it mean physically? Well, here we are basically saying that the probability that the particle goes from A to B is the probability that, A to B in time t, is the probability that it goes from A to Q1 in time t over 2 to Q1 to B in time t over 2. That's what we're saying here. That's all we're saying here. The probability that it goes from A to B in time t, this is just probability. It goes from A to Q1 in time t over 2 times multiplied by the probability that it goes from Q1 to B in time t over 2. That's a physical picture, a path, basically. You have a path. That's what we're doing so far. So that's cool. Let's continue. Let's add more positions. We don't have to stop at Q1. Let's add Q2 in the mix, right? This is the same thing as the integral over dq2 dq1 of b times e to the minus I h t over 3 q2 e to the minus I h t over 3 q1 e to the minus I h t over 3 times a, right? We can just add another position and add another position, right? And this corresponds to saying that the probability that the particle goes from A to B is the probability that, in time t, is the probability that it goes from A to Q1 in time t over 3 to A to, I should really say A to Q2 in time t over 3 to Q2 to Q1 in time t over 3 to Q1 to B in time t over 3. So we have another path. This path over here. And we can go even further. Let's keep continuing. This is the same thing as the integral over dq3, dq2, dq1 of b e to the minus I h t over 4 q3, outer product of q3, e to the minus I h t over 4 q2, q2, e to the minus I h t over 4 q1 times q1 e to the minus I h t over 4 times a. That's equal to b times a time evolved, right? And this corresponds to saying that the probability that we go from a to b in time t is the probability that we go from a to q4 in time t over 4 times the probability that we go from q4 to q3 in time t over 4 times the probability that we go from q3 to q2 in time t over 4, and you get the idea. We have another path here. We can go even further, but you guys are going to hate me if we just keep going forever and just adding more and more paths to the mix, or more and more points to the mix here. But you guys get the idea. We can keep adding more and more positions as long as we keep adding more of those completeness relations. So we have this one, where's Q3? Q3 and Q3, that's one completeness relation. Then we have integral over dq2, q2, that's another one. Then here we also have, of course, q1. We should really be drawing 3 integral signs here, but if you guys see this, and then like dq21, dq 20, dq 19, all of these s's are might throw you guys off because it's like too much. So instead we use just one integrand, and just let it be implied that we have 3. So here is a triple integral, technically speaking. So you can keep going on and on and on, right? Okay. But let's notice something real quick. Let's note that we're time evolving each term. So this is time evolving this term. This is time evolving this term, right? And at the very end, we have a time slice that's time evolving the A term, okay? So we're going to have one time slice reserved for A, okay? Keep that in mind. We're going to have one time slice reserved for A, okay? So, again, how can we generalize this to, like, an infinite number? Not infinite, sorry. Because infinite isn't what... Because if you say infinite, that's not generalizing anymore. So we want to generalize this into any n number of points, right? Because here we had an n number of points, right? So let me just erase this. Here we had an n number... Sorry, here we had an n number of time slices, right? So we want to do this, what we did right now, but for an n number of time slices. How can we do that? Well, it's pretty simple, actually. We say that b, inner product of b with e to minus I h t over n to the n times a is going to be equal to the integral, let's move this to the left, the integral of dq n minus 1 dq n minus 2 dq n minus 3 ... up to dq1, and then this is going to get a bit messy, but b times e to the minus I h t over n qn minus 1 e to the minus I h t over n qn minus 2 qn minus 2 e to the minus iht over n. Let's just do, I don't want to write too much. Then up to q1. So qn minus 2, sorry, qn minus 2, and then dot 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 up to q1 times q1 e to the minus iht over n times a. So we're going to erase this part. So n minus 2 dot 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 up to q1. And that should provide some more space for us. Hopefully. Nope. Does not provide enough space for us. But yeah, this is how we generalize what we just said. That's the, I hate it when that happens. You have to get just these guys. Here we go. That's the generalization of what we just said for some number n. So it's, yeah. Now, guys might be wondering, what are we doing? What are we doing right here? We're saying that if we have n time slices, that's the equivalent of time evolving each qn up to a. So basically, that the probability that we go from a to b in time t is the probability that we go to a to qn minus 1 in time tn to qn minus 2 in time, t over n, to qn minus 3 in time t over n, so on, up to q1, and then to b. So now we have a general path, a more general path now, instead of a specific one. So here's a general statement, all right? And we just used our completeness relations a bunch of times. And you guys might be wondering, why do we start off with n minus 1? That just comes back to what I was saying before, that remember that we time evolved the last a, right? This is time evolving this a ket, right? So we're gonna have one of those time slices reserved for the final position, that final a position eigenstate, that a ket, right? So we're not gonna start at dqn, because that implies that like the last slice will go to a q, but instead we want n minus 1 since one of those slices is already acting on a. I'm gonna make that much more clear by us deciphering this. So let's choose n to be equal to 2 to show how this formula makes sense. So let's erase these over here. So for the case where n equals 2, we start off with the integral for dq, and what's 2 minus 1? 2 minus 1 is just 1, right? And then we're done. If we had n equals 3, we'd have dq2 times dq1. If we had n equals 4, we would have dq3, dq2, then dq1. Basically, we want to descend up to dq1. But for n equals 2, we already start at dq1, so we're done. Okay, so then it's going to be ket b times e to the minus iht over 2 times qn minus 1, so just q1. And then since we're already at q1, we just have to do this one more time. And then e to the minus iht over 2 acting on a. That's our answer. This is our answer for the case where n equals 2. For 2 time slices, here was our answer. So we can see why we started at n minus 1, because that last slice, that last time slice is going to a. So in this case, if we had n equals 3, that would be the integral over dq3 b e to the minus iht over 3 times q3 q3, then times q3 again, but now we have e to the minus I h2 over 3 times q2 times q2, so we went from 3 to 2, so that explains why we are descending n minus 1, n minus 2, n minus 3, all the way up to 1. So that's the explanation behind the general formula that we have constructed here. Alright, so here is where the magic happens. So we are seeing terms here that are of the form qj plus 1 times e to the minus I h t over n times qj, right? Because for example, like here we'd have here we'd have n minus 1, then here's n minus 2. So if like n minus 2 is j, n minus 1 is just j plus 1, since minus 2 plus 1 equals minus 1. So we're seeing in terms of the form qj plus 1 times the time term, the time slice as I call it, and then times qj. That's a general term that we're seeing here. With the and that term is being like smudged between the B state and the A state. Those are the terms that we're seeing. So if we can actually solve what this term is equal to, we're pretty much done. All we have to do is just repeat that multiple times for all the values of j that we want to consider here. So this is the general expression that we want to actually solve here. All right, so it comes down to just this. So how can we do that? Well, we can use our good old trick, the Taylor series. So let's define some quantity delta to be t minus n, since that's going to be easier to write. This makes this expression become qj plus 1 times e to the minus I h delta qj, right? And if you let n approach infinity, now we do that. If n approaches infinity, then this delta term is going to approach 0. This delta term is going to get smaller and smaller and smaller. So for now, let's work with the case where n is like super big, so delta is super small. Okay, so we know like that if delta is super small, then we can expand our exponential in terms of a Taylor series, where e to the minus I h delta is equal to 1 minus I h delta. And this kind of makes sense, right? Because here's an example. Say we want to find what e to the x is going to be. The whole Taylor series is actually 1 plus x squared over 2 plus x cubed over 6 and so on. But if x is like really small, then e to the x is just 1 plus x if x is like approximately 0. The reasoning is that we can say that e to the x is just 1 plus x times 1 plus x times 1 plus x and so on, right? Just multiplying 1 plus x by itself many times, right? That's like the general formula for like e to the x. But if x is like super, I should really, I'm kind of abusing that here. I should really say, pardon me, I should really say that this is just x, 1 plus x to the n times 1 plus x to the n times 1 plus x to the n. Because e to the x, like the actual definition for e to the x is really just 1 plus x to the n to the n. Since e is just 1 plus 1 over n to the n, the limit as n approaches infinity, I should really say that, e to the x is just 1 plus x over n to the n as n approaches infinity, right? So that's just this times itself multiple times. Now, if you want to let n approach infinity, this is basically saying that e to the x is just 1 plus an infinitesimal. Let's call it delta. So 1 plus delta times 1 plus delta, and so on, right? So if you want to find e to the delta, well, that's just going to be 1 plus delta, right? And so we can just stop at 1 plus delta if you wanted to find like e to the x, where x is small. We just stop at the first term, and we build all the other terms by just constant multiplication. I hope that makes sense. So since we're letting delta be really small for our time slice here, the Taylor series expansion is just going to be 1 minus I h. I think I wrote a delta here. It's just 1 minus I h. Okay? So this means that qj plus 1 times e to the minus I h delta qj is just going to be equal to qj plus 1 times 1 minus I h qj. So far, so good. Let's erase this over here. And now this is just going to be qj plus 1 times qj minus I times qj plus 1 hqj. All right, and we have to find out what, we just have to calculate this. Now we actually already know how to solve for this over here, right? This is just going to be a delta function. This is, so we have two expressions basically. We have qj plus 1 times qj that we want to find. Then we want to find what qj plus 1 times h times qj is. We already know this one right off the bat. We know that's just a delta function of qj plus 1 and qj. And we know that it's the delta function because these are positional eigenstates. And this function tells us that if we know that a particle is in point A, then it can't travel to point B instantaneously. So that's why it's a delta function. So this is where we use a trick that might seem a bit weird at first, but when you think about it, it makes a lot of sense. So we can actually write the delta function as the Fourier transform of a plane wave, right? So we know that delta of qj plus 1 and qj is just the integral over dp over 2 pi e to the ip qj plus 1 minus qj. Okay. Let me think. Why did I write this as minus qj? So this would be dqj plus 1 minus minus qj. And then j plus 1 minus qj. I would ask a comma, it should be a minus. Okay. Now you guys might be wondering, how is that equal to that? Like what's going on? Remember this from quantum mechanics. This was probably getting in your head, that an infinitely sharp function, that being the delta distribution, it can be written as a sum of plane waves with a different wave number k. Right? That's like that's a really big thing in quantum mechanics. This is just a true thing about functions in general. We can decompose a function in terms of these oscillatory waves. So all we're doing here is we're saying that this delta function is just equal to summing up a bunch of plane waves together with a different momentum k. That's all we're doing here, right? And yeah, this shouldn't really be anything new, technically speaking. to you guys, but if it is new, there you have it. And we can say the same thing about a momentum wave. The momentum wave, a plane wave. We can get a plane wave by summing up a bunch of like delta functions together, to get a plane wave. That is what we are doing here. So we're writing this in terms of plane waves, and yeah. Okay, so that part is usually what like kind of throws off people, but all we're saying is that the delta function is just the sum of plane waves. All we're doing here. Okay, so now we're done for the first part. We've evaluated that. Now for the second part. This part's gonna be a bit more tricky. We want to find out what this is equal to. First off, we can expand the Hamiltonian out, which would be a good idea. Just expand out the Hamiltonian as the momentum operator squared over 2m plus our potential v, acting on qj. Okay, now there's a problem that you guys might have spotted already. Here we don't have any integral over dp, or over momentum. For the delta function, we had an integral over momentum, right? And we are subtracting the delta function by this term. So this term has an integral over momentum, but this term does not, right? So it's gonna be hard to subtract them from each other. So it'd be really nice to get the second term in terms of a integral of a momentum. So to do that, we could just switch from position space to momentum space, right? And to do that, we can again use our completeness relation. But instead of using dx times the outer product of the position states equals 1, we can instead use the integral over dp of the outer product of momentum states equals 1. So we're going to use the latter instead of the former to change our basis pretty much, all right? So this is just going to be equal to the integral over dp. We should have added dp divided by 2 pi, by the way. 2 pi is there for convention. So dp over 2 pi p. You should have a p subscript j, but like honestly, that it's annoying to write that each time, so we're just gonna write pj at the end. So p times qj plus 1 times p squared over 2m plus v qj, and then that p. So here is the completeness relation. All right. So we can just distribute this momentum state into our term. Oops. I should really put parentheses around here. So doing that gives us integral dp over 2 pi of qj plus 1. I'm getting pretty tired now, a lot of writing. P squared over 2m acting on the momentum state plus v acting on the momentum state, right? And then, times qj times p. So we want to find out what this is equal to. We know that p hat times p equals p times p by definition, right? So p squared is just 2 of the momentum operators, right? And they're acting on this state, this momentum state, right? So that's just going to be p hat times p, which is p times p hat times p, which is p times p times p, or just p squared p. All right. So this means that this is just the integral dp over 2 pi times qj plus 1 times p squared p vector 2m plus vp, and then we had that qj and that p at the end. So now we have like switched to the momentum space. So now p hat, now like our momentum is no longer an operator. Now we just have a nice smooth variable of momentum. We no longer have a p hat here. All right, so that's going to be very convenient for us since our Hamiltonian will also not be an operator anymore. So we can now just take the p out of the parentheses that should be there. If I was paying attention, or they're kind of there. Yeah. So and that's going to give us an integral dp over 2 pi qj plus 1 p times p squared over 2m plus v, and then p acting on qj. Right, so really we're going to, yeah, all we did here was we just took this guy out here, and then we took this guy out here, sort of. Really, technically speaking, we took this out here, and then we moved it here. So hope you guys are seeing like which one is acting on which one. This one is acting on this one, actually. And then this one is acting on this one. That doesn't really matter that much, right? So now this, all we are doing is we're letting our momentum states act on the position states. All we're doing here, all right? So now we can use the cool property that qj plus 1 acting on p is just the integral. Did I forget? I did not forget what this is. No, I forgot. This is like a staple thing in quantum mechanics. And I didn't forget. It's just e to the I p qj plus 1. So then what's p and a product of p and qj? You ask? Well, since qj acted on p is e to the I p qj, this means, and we know that the complex conjugate of this is going to be p acting on qj, so that's going to be e to the minus I p qj. So this is going to be e to the minus I p qj. All right. So this expression becomes the integral over dp over 2 pi e to the ip times qj plus 1 minus qj. Just combine both of these terms together. And then times p squared over 2m plus v, which I'm just going to call the Hamiltonian because it's faster to write. That's just going to be h. And we finally wrote it in terms of momentum, so that's cool. So in short, we wanted to find out what this is equal to. Oops, yeah. What this is equal to. And we found out that this, which is the integral over dp over 2 pi of e to the I times qj plus 1 minus qj, and this is equal to this over here, the integral over dp 2 pi e to the I, oh, sorry, I forgot to add the p here, e to the I p qj plus 1 minus qj times h. Oh, that's weird. It's a car that's making noise. So that's just going to be the integral over dp. Yeah, that is really loud. Ignore that. Over dp over 2 pi e to the I, this was p here, by the way, e to the I p qj plus 1 minus qj minus I times the integral dp over 2 pi e to the I, running out of space here, I apologize, e to the I times p qj plus 1 minus qj times h at the end. So now, we can just factor out, the common exponential integral part to get this. Is just the integral dp over 2 pi e to the I p qj plus 1 minus qj times 1 minus ih. And what do you know? This was just e to the minus ih delta, right? But Taylor expanded. So we can now write this as integral over dp over 2 pi e to the ip times, can make this a bit closer, e to the ip qj plus 1 minus qj. This is just a bunch of math now. There isn't really a conceptual thing behind this. This is the boring part, just number crunching at this point. We can just factor out, I'm not going to write this whole thing again. We'll just factor out the I to get p times qj plus 1 minus qj, and then minus h delta. We can then factor out the I delta to get p times qj plus 1 minus qj over delta minus h. And if we let delta become really small, which means that n gets really large, this just becomes the derivative, right? So you have e to the I delta times pq dot minus h, which, oh my gosh, look at that. That's just the Lagrange transform of the Lagrangian. This is just ei delta times our Lagrangian. But in our video, we aren't going to go that far. We're just going to leave it as this over here. And surprise, we're actually kind of done. So remember, we were trying to calculate what qj plus 1 times e to the minus ih delta times qj is. And we just found out that it's equal to the integral. Now we can add the pj at the end, right? So dpj 2 pi times e to the I pj times qj plus 1 minus qj e to the minus ih delta. So our answer, remember how at the start, let's scroll a bit back, right? We found out, right, that the general form looked like this, right? And we were integrating over dq, right? So now our answer for the probability that the thing goes from a to b is now going to be the integral. Let's just use a symbol. Let's call it, I don't know. Let's call it gamma. Gamma seems kind of cool. I don't like gamma. Let's just call it the probability. Probability that it goes from a to b. So write it like that. It's going to be the integral over, so you have j equals 1 up to n equals 0, the power, the pi symbol, dqj times the integral dpj over 2 pi of e to the I times pj times qj plus 1 minus qj over delta. Oh shoot, we forgot to add a I delta term here. So I times delta of that minus h. Yeah, that's cool. Let's make this a bit more aesthetic. I delta. Because again, we found out that the general form for the things that were being sandwiched together, these things was this. So the answer to the probability is just this, and they have to add in the integrals over positions at the start. So here, this is our answer to the probability that a particle propagates, big words, aren't the big word, but from point A to point B in time t. It's just the probability that the particle takes each possible path multiplied together. Because that's what this is doing here. Because as we let delta approach 0, what we're doing here is we're building all these different paths together. So we have, here's A and here's B. Well, let's let B over here. The probability is just, we're just taking each of these paths and we're pretty much like, people will say summing together. I think a more appropriate term is multiplying them together. And we're multiplying like each of these paths together, connecting the points, you know. We're looking at paths where like the particle goes like to the moon and back in a fraction of a second, which is unphysical, which doesn't happen, of course, right? We're taking a bunch of these different crazy paths to get our probability. Now, this is me personally. I don't like this. When I hear someone say taking a bunch of these different paths, it gets confusing, right? Like, you're like, how's a particle taking all these paths? Like, how is the math actually saying that? So I like to think of this path integral formulation as simply a mathematical formulation of quantum mechanics from which we can make pictures in our heads of a bunch of these different crazy paths. But we should know that the math isn't saying that it's taking all these different paths. The math is just saying, do this to calculate the probability. So we shouldn't interpret this as saying that the particle just splits up into clones and takes all these different crazy paths. Instead, we should think of this as a tool used to calculate probabilities. And with all that being said, we're pretty much kind of done here, honestly. What we can do, a lot of people like to also, I think like there should maybe be a j equals 0 to n minus 1 summation thing over here. I'm not completely sure though. But what people like to do is they like to define what's called the path integral measure, which is like a weird q, which is defined as being this thing that you see here. And a similar thing with p, I like writing it in terms of a weird dumb thing that you see here. So this being written in terms of the path integral measure will just be the integral of this, and then here we have the p. I'm going to ignore the 2 pi for now. And then we'd have e to the I, and then the delta things that you see here. What you'll see being used a lot is the action. We say E equals the time integral of the action. But we have to do some more steps to sort of derive that last step. But yeah, that's if you'll see the path integral being written in terms of these weird curly D's. That is what they mean. So here is the formula for the path integral. I'm gonna check with my notes to see if I am actually writing it correctly. Yes, I am writing it correctly. But yeah, we just had to, technically speaking, we have to insert a sum. We have to insert another sum here. That's what my notes say. We are doing this. Then we have to sum from j equals 0 to n minus 1, and then times that. So I'm just trying to get things in the right final form. Okay, so yeah, here is our formula for the path integral. And with all of this, we're done. There isn't really much more to say. We can, of course, integrate over the momenta at the end, but that's for the next video. So here is the path integral. And we would solve this integral to find the probability that it propagates from point A to point B. So, yeah, that is pretty much it. And yeah, I hope that wasn't too hard to follow. I know that some parts can still be confusing. If you guys don't get the path integral, if you don't understand it, then like don't worry about it. It isn't a big deal. Like it took me a year to understand the path integral. Like not literally a year. Like it's not like I was trying to learn it for a year straight. But I've been visiting it like every now and then, and I've been like, this doesn't make any sense still, right? But it's something that kind of takes time to sort of accustom to. There's this quote that's like, you don't understand math, you just get used to it. I hate that quote. I think you can't understand math, but for a lot of the time you just have to like get used to it, and then you'd actually understand it. So if you don't understand any of this video, that's okay, right? You can always use the canonical method in quantum mechanics. That's fine. But the path integral, while it is pretty crazy, it's a unicorn for sure. It's a really great way to study quantum systems and get a lot of information from them. So with all that said, thanks for watching and have a great day. I'll see you guys another time. Till next time. Bye.